Hey there, and welcome to The Explainer. Today, we're going to dig into a concept from pre-calculus that is way more powerful than it looks, the inverse matrix.
All right, to really get this, let's start with something you already know super well. Think about the numbers 4 and, say, 1/4. What's the deal with those two?
Right? You multiply them together, and what do you get? You get 1. That's what we call the multiplicative identity. And because of that, they're multiplicative inverses of each other. It's a pretty simple idea, right? One number basically just cancels out the other through multiplication.
So that begs a really cool question. Can we do that same thing, but with a whole grid of numbers? You know, with a matrix? Is there a matrix out there that can undo another one? And the answer is a huge yes. And believe me, it is an absolute game changer.
So here's our game plan for this explainer. We're going to look at the matrix reciprocal, meet the identity matrix, see how inverses solve systems of equations, figure out how to find them, talk about when they don't even exist, and then wrap up with a cool little matrix curiosity.
Okay, first up, let's get down to the core idea. And you'll see it's a perfect parallel to those numbers we were just talking about.
So this thing is called the inverse matrix. You'll see it written with a little superscript -1, kind of like an exponent. And the idea is super simple. When you multiply a matrix, let's call it A, by its inverse, you get the matrix version of the number 1.
Right, so I keep saying the matrix version of 1. What in the world is that? Well, it's got a special name.
It's called the identity matrix, and you'll usually see it written as a capital I, and it's pretty easy to spot. It's always a square matrix, and it has this clean line of ones running from the top left to the bottom right. That's the main diagonal. Everywhere else, just zeros. And this is that special matrix, that target we're aiming for when we multiply a matrix by its inverse.
Okay, but why does any of this matter? I mean, what's the point of finding an inverse in the first place? This isn't just some neat math party trick. There's a real superpower here.
And here it is. Their biggest, most powerful use is solving huge, complicated systems of equations with, like, simple algebra. We're talking about the math that powers everything from your favorite video games graphics to complex economic models. And trust me, solving those things by hand is a total nightmare.
And this slide just lays it out so perfectly. Look on the left. That's basic algebra, right? To solve for x, you just divide by a, or you multiply by its inverse. Well, look on the right. We do the exact same thing with matrices. To find that matrix x, all you have to do is multiply matrix B by the inverse of a. It takes what could be pages of work and boils it down to one clean, elegant step. Pretty amazing. Okay, so now for the million-dollar question. How do we actually find this thing, this magical inverse matrix? Well, there are basically two main ways to go about it.
First up, we've got the old school method, doing it by hand. And it involves this really clever trick using that identity matrix we just talked about. Okay, so it's basically a 3-step dance. Step 1, you create what's called an augmented matrix. You just take your matrix, A, and stick the identity matrix right next to it. Step 2, this is where the work happens. You use these things called row operations. You can swap rows, multiply them by numbers, stuff like that. And your goal is to turn the left side of your setup into the identity matrix. And step 3, this is the magic part. As you're doing all that work on the left side, the right side automatically, like magic, transforms into the inverse matrix you were looking for. It just appears.
Now, a little word of warning here, and this comes straight from the source material. Get ready to get your hands dirty. Fractions are usually unavoidable. So yeah, expect things to get a little messy when you're doing this by hand.
But thankfully, you don't always have to do that. There is a much faster way, especially if you want to check your work or you're dealing with a really big, nasty matrix. And that, of course, is using your calculator. It makes life so much easier. You just enter your matrix, find that special inverse button, usually it looks like x with a -1 exponent, and hit it. Now, this is really, really important. Do not just use the regular exponent key and try to raise the whole matrix to the power of -1. That's a totally different operation in matrix land, and it will give you the wrong answer. Oh, and a pro tip, store your result. That way you can use it in other calculations without having to type it all in again. Just be ready. The calculator might spit out a bunch of decimals, and you might have to scroll around to see the whole thing.
So, this all seems pretty straightforward, right? But what about the exceptions? The matrices that just break the rules? Turns out, this whole process doesn't work for every single matrix.
Yeah, do they all have an inverse? The answer is a hard no. It's kind of like how the number 0 doesn't have a multiplicative inverse, right? You can't divide by 0. Well, some matrices are the 0 of the matrix world, and there are two big reasons a matrix might not have an inverse.
First off, the matrix has to be square. That means it has to have the exact same number of rows as it has columns. So a 2 by 2, a 3 by 3, that's fine. But a 2 by 3? Nope, no inverse for you. The second reason is a bit more mathematical, but it's a huge deal. Its determinant can't be 0. Now, the determinant is basically the special number you can calculate from any square matrix. It tells you a lot about it. And if that number happens to be 0, game over. The matrix is called singular, and there is no inverse to be found. Period.
All right, now for something really cool, a bit of a fun fact. There are some super special matrices out there that are, well, they're their own inverses. They don't need anyone else to undo them.
I mean, the identity matrix is the most obvious example, of course, but there are others, like the famous helmet matrix. It's this really clever, specially designed matrix where, if you multiply it by itself, you get the identity matrix back. It's literally its own mathematical mirror image. How cool is that?
And that kind of brings us to one last really interesting question to chew on. We made a big deal about how non-square matrices don't have a regular inverse, but the source material hints that they can have something called left or right inverses. So what's up with that? What kind of new doors does that open? What new kinds of problems could those things help us solve? It really makes you wonder, and that's a fantastic place to explore next.